In this activity, we'll place strings of various masses under calculable tensions. We'll pluck the strings under tension while recording the sound they make using a sensitive microphone. From analyzing recordings of the audio, we'll be able to determine the fundamental frequency of each string under each different set of conditions. We can determine the factors that influence the fundamental period and frequency of sound that a string under tension makes. The first step of this lab is to acquire the wire to be tested and determine its linear mass density. The formula for linear mass density is mu equals m over L, where mu stands for the mass density, m is the total mass, and L is the total length. Let's try that for a wire now. Okay, so here I have a length of wire. This is going to be my thick wire. I also have a thinner wire here. So we have two different linear mass densities. So one of them is the thick and the other is the thin. So the thick wire is 18 gauge and the thin wire is 28 gauge. Now when you're doing this activity in a lab, it's a good idea to have enough wire so that your wire can go across the table and touch the ground on both sides. And you might want a little more wire than that even. You just don't want the wire to be too short. So I have two different coils of wire here. One is a thick gauge. It's an 18 gauge, this one here. And this one is a 28 gauge, thinner wire. The first thing I'm going to do in this lab is test the difference that linear mass density makes when it comes to the sound of a string. So I'm going to first determine what the linear mass densities of each of these coils is. And that'll require getting their masses and their lengths. The thin wire has a mass of 4.3 grams. The thick wire has a mass of 9.0 grams. Let's write those down in the data table. Now I'll need their lengths. Okay, so I've got the thick wire here. I'm gonna uncoil it. I'm gonna really try not to put too many kinks in the wire. The problem with the wire is that it can break in this experiment, so that's just something to be wary of and just try to avoid. And any kind of sharp folds in the wire just really don't help. So I'm just gonna kind of unwind it carefully here. Okay. So we'll see how many meters it is. This meter stick has some holes in it. So I'm gonna lock the wire into the holes. Like this. There we go. and I'll just feed it through. It's got a hole on the other side too. Okay, there's 1 meter. It's pretty stiff wire here, but that's what we want. Okay, so that's about 3 meters worth of wire right there. All right, let's write that down. Now let's get the thin wire's length. That one should be a lot more flexible. Okay, that's about 3.5 meters. Maybe 3.4 meters. Alright, so let's divide now to find the linear mass densities of these wires. I get 1.26 grams per meter for the thin. Let's say 1.3 grams per meter. And I get 3 grams per meter for the thick. Alright, there we go. So for this first experiment, we want to only vary the linear mass density and keep everything else in the experiment the same. So how it's going to work is we're going to hang masses from 2 sides of a wire. We want the forces to be balanced, so the masses should be equal. So what I've made is this PVC pipe apparatus that will help us to put tension on the string. So my PVC pipe apparatus fits perfectly across this lab table. What I'm going to do is I'm going to run the wire from one side of the PVC to the other, putting it into these T-joints here, and then what we'll do is we'll hang masses below. All right, the first thing to do is make a loop at each end of the wire, and it's important that you make it sturdy enough so that it's not going to come loose even if we put a lot of weight on it. So I would recommend just winding it around several times. Really twisting it. So if you can see what I'm doing here, I'm trying to make a loop that I can hang masses from, but I really need to wind this many times, perhaps even going through the middle of the loop like that, and then just really winding it some more. You just don't want this to slip. That's a common problem that I've seen with this. Okay, that looks pretty sturdy. So that's gonna go in one end, and then you just need another loop for the other end. Now you want to measure it off so that You really want your masses close to the ground for this. I've done it a few times now, this lab, and what can happen is the wire will break over time. You put enough mass on it and you do it enough times, eventually the wire's gonna break. So it's really good if the wire is hanging such that the masses are really right next to the ground. So if it does break, it's not going to land on anybody's foot, and it's not going to land on anybody's laptop or anything like that. So let's see if we can measure that off. Let's see if we can make sure that there's enough wire here so that we can be close to the ground but not touching. So now let's hang some masses. Okay, so I'm gonna try to hang a mass from the left side and a mass from the right side. The wire might hit the ground here, not sure. Okay, looks like we're all set there. So I've got one mass hanging from the left side and one mass hanging from the right side. Now there should be some tension on this string. I doubt it's enough to really produce an audible sound. We can see it vibrate. Yeah, so we see the thing vibrate, but it's just not enough to make too much of a sound. So let's put some more mass on it. I'll put another 2 kilograms on. There's a lot of friction in this setup. Okay, now we've got 2 kilograms of mass on each side. So let's see if that makes a difference in the sound. Yeah, it's a little bit better. It's a little bit better, but the fact is we can hang a lot more mass on this wire. Since the weights are close to the ground, there's not really much danger involved. So let's put some more mass on. Okay. Yeah, now I'm starting to hear a pretty distinct tone. I'd still like to get the pitch up a little bit higher though. Okay, I've got 4 kilograms on each side. And the pitch is getting higher. Let's try some more. Okay, so that's pretty good there. I'd like to get a sense of what the fundamental frequency is right now. So I'm going to record it on Audacity, see if I can determine what that pitch is. And it does help, honestly, to do a few trials where you have less mass on at first and then add more mass. So right now I got a total of 6 kilograms on each hanging strand. All right, so let's record the sound now. Start a new track. Okay, so I have this external mic here that I can use to capture the sound a little bit better than the laptop could do itself, because I could put the external mic really right next to the string. That thing looks kind of creepy. Looks like a killer robot or something with that red eye. Okay. Now there's a little bit of a background HVAC going on here in this room. There's some airflow. It's making a little bit of noise. Like even if I just record without speaking, you know, we can see that there is something going on in the background. Let's see what it sounds like. Yeah, so there's a clear oscillation to it. Yeah, so I don't think I'm going to be able to turn that off, but hopefully the signal from the string will be loud enough that it won't make a difference. Okay, are we ready? I'm going to pluck the string. Okay, so it looks like that is all I got. That's pretty weak there. We need a lot more signal to noise ratio. Right now, the signal is getting lost in the noise. Yeah, so let's see if I can actually put the mic right up to the string. That should help. Okay, so right here is a sample of it. I can zoom in. Okay, I do see an oscillating pattern. I want to make sure that's not just the background noise though. Now we could do a calculation of the period here. The period is 37 minus 19. That's 18. So the period is 18 milliseconds. So let's just do 1 over 0.018. The frequency might be 56 hertz. I think that is in the range of what I'd expect for a long string like that. That's thick and under not that much tension. However, let's use the FFT analysis. Oh, that's just the noise. Yeah, so as we can see, that background noise is pretty extreme where I am right now in the lab. Let's see what kind of FFT we get. So for the FFT, go to Analyze and then Plot Spectrum. Okay, so we do see a very big peak at 58 hertz. There's another peak at 118 perhaps. Let's try a different sample size. Okay, we got a peak at 56, a peak at 216, peak at 214, peak at 60. Alright, now let's sample just the background noise just to see, like, what is the frequency of that hum of that HVAC equipment in the background. Okay, unfortunately, it's a huge 58 hertz hum. And that 58 hertz is not due to me playing the string. So that's a real problem for where I am right now. I might have to change locations to somewhere quieter. I don't see how we could avoid it. Okay, let's move somewhere quieter. Okay, I'm back. I moved my experiment to a different part of the room. I got myself away from that air vent over there that was pumping out 58 hertz tone. Yeah, you can't have that interfering with the experiment because I'm looking for a fundamental tone around that same frequency. But that's just a part of, recording too. Like, if you've ever done any music recording, you know. A lot of times when you're recording music in the real world, you're trying to get away from unwanted noises. It's not easy. So okay, the vents are still over there, but they're a lot farther away instead of just directly overhead now. So we can try the experiment again. I've got the mic here. Gonna hold the mic up to the wire. Let's see if we can get a better signal to noise ratio this time. Yeah, that one doesn't look too bad there. He's not too bad, but I'd still like to boost him up more. Let's see what the frequency, let's see what the FFT says here on this. Okay, 56 hertz. Yeah, 60 hertz, okay. Yes, it's still kind of weak. So what I have here is a guitar. Guitar is very capable of amplifying strings. So what I'm going to do is I'm going to touch the guitar to my pipe at the same time that I'm playing the note. And let's see if it can improve the loudness of it. Here it is without the guitar. Now let's try it with the guitar. It's definitely better. Let's see if we can do that. I'm gonna lay the mic down. I'll lay the mic down right next to where the guitar will be. And let's try it again. Much better. Okay, so that's a good sample there. That looks like a good one. Okay, so let's zoom on this. We got a lot better signal to noise ratio this time. We can see here that the string signal is much louder than the background noise this time, thankfully. What we're looking for is a repeating pattern. Now, I could say that this is a start of a cycle, and it might be tempting to think that that's the end of one. However, if you notice here, there's a pattern occurring where we have a short peak and then a tall peak, and then a short peak and then a tall peak. So the periodic nature of that makes me think that really this is probably the entire cycle. So if I was to just get this, I'd probably be not getting the fundamental frequency. Just out of curiosity, if we were to subtract here 52 minus 49, that's a 3 millisecond period for that particular curve. Let's just see what that frequency would be. 333 hertz. Now, I definitely know that this string is not at 333 hertz. The low E on a guitar is 83 hertz. So, here's the low E on a guitar. Here's this thing. It sounds lower. I feel like I'm watching Jaws. No. Yeah, you know, it's similar. It's a similar pitch, I think. I think it's just maybe a half step or a whole step below the low E. So I bet we're looking for something just a little bit less than 83 hertz. Now, if we do this, that period is 56 minus 49. It's going to be 7 milliseconds. That's 143 hertz. With these waveforms, sometimes looks can be deceiving. You might think you have the lowest frequency, but maybe in some cases you don't. Let's do the next best thing, which is to look perhaps somewhere else in the wave. Now that's a pretty short burst there. I did get a couple different samples. Let's try a couple other samples. Let's see what those show us. Okay, here's one. It's just a little tough to tell. Let's try this guy. $309, 150. Okay, here's a big peak at 56, a big peak at 155, and a big peak at 311. Okay, so these harmonics that we see, oftentimes they're going to come in ratios of being a multiple of each other. What we're going to see is that for our fundamental, the next harmonic above him is supposed to be double of the fundamental. And then there should be another harmonic that would be double of this harmonic. And we do see that here. We've got a note that's around 155 hertz, and then if you double that, you get to 311 approximately. So that makes sense that these two harmonics do come from my wire. This one here, though, is probably just the background noise. Let's try the other one. Okay, I see a harmonic at 158 and 316. Now half of 158 would be 79. I'll bet that there's supposed to be a peak in here at 79 for the lowest frequency. So when this kind of thing happens where it's kind of inconclusive, you'll likely want to just put more mass on the thing and raise the tension in the string. So I've got more mass that I can put on. Okay, so let's put some more on. Okay. All right, so that is 7 kilograms on each side. Let's listen to see if the pitch had changed. Maybe a little bit. Let's do 8. Okay. You can hear it going up in frequency. So with a higher frequency, I hope that it'll come in a little clearer. Yeah, that last one was pretty good. This one. Yeah, so let's check out this one. Now, since I had put more mass on, I'm thinking that the frequencies that we see should be just a little bit higher than the ones we saw before. That can help you zero in on the right frequencies. Now this one's pretty interesting in that I see we have a super tall peak here and some other little peaks and another super tall peak there. That leads me to believe that the fundamental frequency is actually this entire thing. Now, let's see how many milliseconds that is. 205 minus 194 would be 11 milliseconds. Before I had only 7 milliseconds. So now we're getting a frequency of 91 hertz there. I think it's possible that really is the fundamental frequency of that note. So in order to compare it, let's listen to the low E again. And now let's listen to the string. I think they're similar. Oh, you know what's funny? This whole time I've been recording, I never turned on the other mic. Okay, hold on now. We don't need it. Okay, we don't need it. Let's do the FFT now. There's a peak at 177 there. That one's unclear. I see a peak at 176. And then there's a peak at 58 as usual. And another peak at 85. I think the 85 is the actual fundamental frequency of my note. It's just that it's getting confused with the background noise. But one thing I realized just now, unfortunately, was that the system wasn't using the external mic all along. It was just using the laptop mic. So let me see if I can quit Audacity and bring it back. You have to completely quit Audacity to get it to recognize new mics. I've noticed that. Alright, we go to the audio setup, and now the snowball is showing up on the list. That's a problem, is you can't just plug it in and expect it to automatically be enabled. I should have realized that. Okay, let's try this again. Yeah, so I'll try it with no amplification first. That looks like a much cleaner signal. I could probably do it just off that, but let's see how it is with amplification. Wow. Alright, so now there's no question. We should be able to get a good reading out of this. Okay, the signal is so much cleaner than before. You can really see the repetition here. And I'm thinking that an entire cycle just starts here with a big peak, and then it goes to the next big peak. Something like that. So 54 minus 42 would be 12 milliseconds. Similar to what we had before. So it's an 83 hertz signal. Just out of curiosity, let's also record the guitar low E for a moment, because I feel they're so similar. And let's check out the waveform of this. I feel like they're the same note practically. Okay, so there's this this dip right here that I also see appearing here and here in a rhythmic pattern. So I believe that if we go at the end of a dip to the next end of that big dip, that's probably the fundamental frequency. So it's 75 minus 63. What do you know? It is 12 milliseconds. And we know that the low E is supposed to be 83 hertz. So this matches up quite well. You could play them both at the same time and hear they're right in line with each other. He's a little sharp. Alright, so that settles that. We got the fundamental frequency on this guy. So what we need next is we need the thin wire. Keep in mind that I did put a lot of tension on there. That's 1, 2, 3, 4, 5, 6, 7, 8 kilograms on each side. I don't really know if the thin string can handle that much? Guess we'll find out. Okay, so I'm going to attempt now to move the old experiment out of the way, and we'll replace it with a brand new pipe of the same length, and we'll do the thin wire on the new pipe. Okay, now I just need the wire. Another thing I've been doing is putting tape on the inside of the edge of the PVC there. Just trying to cushion it a little bit so it's not hitting like a hard, jagged edge of the plastic PVC. Might help a little bit, because in the past when I was first trying this out, it did break at that junction where the wire wraps over the PVC. So I'm gonna hang the first kilogram. So I have 1 kilogram hanging from the thin string. And let's see if we can get some more on there. So that's 3 kilograms on each side. And we're already getting a pretty good note out of that. Now the other strand, the thick string, has right now 6 kilograms each. This guy's got 3. So maybe we can find a middle ground where they each have the same number, like let's say 4 on each or something. Doesn't feel like it's gonna break yet. Okay, so I've achieved balance here. So I was able to hang 4 kilograms from the thin string here in front, and also I'm hanging 4 kilograms now from the string in the back. So let's compare the sounds and see which one do you think is going to have the higher pitch, or would they have the same pitch? Let's find out right now. Here's the thicker string. Here's the thinner string. Again. To me, it sounds like the thicker string has the lower frequency. But let's use the mic and see if we can prove that. Okay. First I'll pluck the thick string. Now the thin string. Okay, so let's see the results. First I'll pluck the thick string. Okay, so this is our thick string sample. Now we see this kind of Stegosaurus pattern here. let's see, we've got 2 peaks and then a big drop. Here's another 2 peaks and then a big drop. 2 peaks and a big drop. I see a pattern. 2 peaks, big drop. 2 peaks, big drop. So I think if we just go at the start of those 2 peaks and go to the start of the next 2 peaks, that should do it. So 398 minus 384, that makes 14. It's not a surprise that the pitch of the thick string went down. It's now 71 hertz, whereas in my last trial it was an E, basically. It was 83 hertz. Now it's down to 71 because I took some mass off. Now let's go to the thin string. See if we can determine what its frequency is. Now the thin string. It's a pretty good sample. And yeah, it's a pretty clean waveform. You can clearly see what the pattern is here. It doesn't look like there's anything unusual about it. I think this probably is the fundamental period right there. 1 cycle. So that's 70 minus 58. That's 12 milliseconds. And just to be sure, let's go. We could go for 4. So this looks like 44. And yeah, you divide by 4. Okay, so it's about 11 milliseconds for 1. Okay. Okay, so perhaps 91 hertz for the thin string. Let's compare it to the guitar and just see if that makes sense. Okay, so here's the low E on the guitar. And then here's the thick string. Yeah, I think this is about a 1 step below this. It's probably about a D here. And let's listen to this one. Yeah, so it's almost, I think, 2 steps above low E. Yes, this is about a F sharp. Little flat. And this is about a C sharp. Yeah, now they match. Yeah, they match pretty well there. Okay. So let's write down the final results. After all my practice and trials, I ended up hanging 4 kilograms from the left side of the thin wire and 4 kilograms from the right side of the thin wire. I also made it so that the thick wire mass ended up matching with that. So it was 4 kilograms for everybody. When it comes to the vibrating string length, I can measure that now. I'll just get a meter stick. Okay, now I want the effective length of the string, the part of it that's allowed to vibrate. Looks like about 91.5 centimeters. I'll put it in meters though. It's about 0.92 meters. Well, when it comes to the calculated string tension, I've got 4 kilograms hanging from the left side and 4 kilograms hanging from the right side. According to Newton's laws, the forces have to be balanced in this situation because our object is at rest. So this means that the force of gravity, the weight of the thing, has to equal the tension in the string for both of these objects, actually. So weight has a formula of being the mass times g. So in this case, our mass is 4 kilograms, and we'll multiply by 9.8 newtons per kilogram. That's the acceleration due to gravity near Earth's surface. So this weight is 39 newtons. And therefore, according to Newton's laws, the tension in the string must also be 39 newtons, and it would be the same on both sides. This actually doesn't double the tension or anything. It's just going to be that the string tension is the same on the left as it is on the right. Now that should be the case for both systems, actually. Now when it comes to the fundamental frequency, according to the calculations, I had 71 hertz for the low note, and the low note was the thick string. The high note had a frequency of 91 hertz, and the high note came from the thin wire. So I think this experiment pretty conclusively shows us that the lower the linear mass density is, the higher the frequency can be. Or you could say the heavier the string, the lower the note. So a lower linear mass density results in a higher frequency of pitch. A higher linear mass density results in a lower frequency of pitch. The next investigation is, how does wire tension affect frequency? So just from our recent trials here, I have a sense of how it's going to turn out. So right now, on my thin string, we already calculated that the thin string has a linear mass density of 1.3 grams per meter. And we'll let that be the same for both trials because I'm going to use the thin string both times. Because in order to really compare wire tension, we have to use the same string. It wouldn't be fair to change the wire tension and change the style of string as well. That'd be a confounding situation. We want to keep everything the same now and just vary the wire tension. So I have to pick one of the strings to do it with. I'll just do it with the thin string because I feel like we get a little bit better signal out of him because the note is a higher pitch. So in the one case, I'm going to let there be 4 kilograms on either side of the wire, and we already know from our previous calculations that that's 39 newtons, and I'm going to keep the same string length as before, 92 centimeters. The fundamental frequency for that situation ended up being 91 hertz. So let's see what happens if we vary this. We could do a couple of trials. Let's try it with 5 kilograms on either side. Right now there's 4 on each. Okay, we've got 5 kilograms hanging from both sides now. Let's try to get the pitch once again. Keep in mind, here was the old pitch. For the old pitch, we had 4 kilograms on each side. And now for the new pitch, we've got 5 kilograms on each side. It sounds like it's 2 half steps higher. It's a higher pitch. Let's find out what its frequency is. May be able to do it quickly with the FFT. Yeah, look at that. Looks like 102 hertz. 101 hertz. The system's very consistent about that tone being around 101, 102 hertz. The old tone, of course, was clearly around 92, 91. So you can see the frequencies shifting as we increase the tension. This will be 49 newtons and 101 hertz. I think what I'm going to do is I'm going to take mass off of the thin string. So I've only got 3 kilograms hanging from the thin string now. Let's see what note that gives us. Okay, so with 3 kilograms on the thin string, we get a peak of about 88 hertz. And let's try 2 kilograms as well. Okay, ready? Okay, that's with 2 kilograms. Looks like 61 hertz there. It's getting a little tough to tell what the pitch is at that low mass. It might be 61 hertz, but not too sure there. Okay. So there we go. Okay, so there's just one last thing to test, and that is, how does the length of the string affect the frequency? I could do that with the thin string here. All I want to do is use a different pipe length and just see if I shorten the pipe, would that change the frequency? Or if I make the pipe longer, would that change the frequency? When the thin string had 3 kilograms on it, we got these numbers. So I'm going to put 3 kilograms on the thin string. I'm going to do it on the short pipe now. So we have 3 kilograms hanging off each side. The length of the pipe is 63 centimeters. So let's see what frequency we get. Okay, let's see what that note is. It appears to be 121 hertz, higher than any note that we've seen thus far. Yep, definitely around 121 to 123 hertz. So when we have 63 centimeters with the thin string, 1.3 grams per meter for the mass density, 3 kilograms on both ends, and 29 newtons, the frequency is now around 122 hertz. We could try one more. We could now try the shortest pipe. Okay, so I've got the thin string and the short pipe, 3 kilograms hanging off both sides. Let's measure the short pipe. The effective distance is 30 centimeters. Let's see what kind of note we get. Spectrum says the frequency is 248 in that view. 248, 246. So I'll go with an average of 245. String length was 30 centimeters. We used the thin string. 3 kilogram mass, 29 Newton tension, 245 hertz. What a change. So clearly, the linear mass density matters when it comes to the frequency. And we see that the wire tension matters. Higher string tension results in higher frequencies. Lower string tension results in lower frequencies. And finally, shorter vibrating lengths result in higher frequencies, and longer vibrating lengths result in lower frequencies.